a block of encoded data qubits, I measure the syndromes in some way, either using STEAM method or the Shor method, cat states or whatever. Now you feed that syndrome information back into your classical computer. You use your classical computer to decode it to figure out what the correction is, and then you apply the correction. Right? So we're doing we have a classical computer working together with a quantum computer. And this is really interesting, right? So the problems like you got to make this classical computer really fast, often, because you want to feed it back into the quantum computer as fast as possible. And decoding classical codes isn't necessarily efficient. Like designing fast decoders is hard, and some codes might not be possible. Whatever. So that's all a trick. In fact, we can do fault tolerance. In principle, we can do fault tolerance without a classical computer. So without any measurements, only using unitary gates. And this, you kind of have to convince yourself that it's true. But like the easiest way of seeing it is you take this circuit and you make this thing unitary, right? Remember how to make a measurement unitary? How do you make a measurement unitary? Yeah. Right. So if you want to simulate a measurement like this. So it takes one quantum wire, one qubit into a classical bit. You can do it just by equals. You can copy it into an qubit, and then throw away the qubit. And then that's essentially this wire now holds the classical measurement results. Once we trace out this extra qubit. All right, so you make this all unitary, but again, that's not fault tolerant because any error in this classical decoder could spread to an error here. It could spread to a high weight error here. And so what you do is you take this circuit and then you only apply the correction to qubit 1. Then you repeat the whole circuit and you only apply the correction to qubit 2. And then you repeat the whole circuit and you only apply the correction to qubit 3. That will be fault tolerant because there's no way for errors to spread, and it's all unitary, so it's fine. Obviously, it's kind of high overhead. And people generally don't bother computing the threshold for these kinds of schemes. If they do, the numbers they get are very poor, like 10 minus 6, 10 minus 8, maybe, I don't know, noise. So hopefully you do have the ability to do measurements and you don't have an all unitary quantum computer, because it's really nice to have classical computers that are reliable. Classical computers are really helpful. Yeah, that's right. Non-Markovian noise. Okay, so we haven't talked very much about this, but so in general, like. Okay, so we've talked about very simple noise channels like polynoise or depolarizing noise, this kind of thing. We've also talked about like cross operators, like general quantum channels, that kind of thing. But in fact, you can imagine even more general noise models where it's not a channel. The noise that occurs is not described by a quantum channel, but instead what happens is you have some interaction going on between your quantum data and the outside environment. And in particular, so this is different from a quantum channel because in particular, the interaction is ongoing. So some of your data can leak out into the environment at time 0, and at time 1, it can come back in maybe. So basically, there's correlations in time that are not accounted for in the channel model. In the channel model, you apply the same channel over and over again. Whereas here, what I'm saying is you have some environment that can store information coherently for a long time. Again, there exist threshold theorems for this kind of model as well. So here, I have a Hamiltonian describing the system, the bath, and some interaction between them. And there's threshold theorems that look like this. So for example, the threshold theorem is depending on the norm of the strengths of this interaction term. There are threshold theorems that hold if you have non-local coupling between data qubits. So you've noise not just on neighboring qubits, but you've noise even on qubits. You've correlated noise even on qubits that are far apart from each other. Provided that the correlations decay fast enough, you can still prove a threshold theorem. It's like inverse polynomial or something would be fast enough. But you get worse numbers, certainly. And then you have other issues, which are that a lot of these, so these kinds of theorems, they give you a threshold in terms of the norm of the Hamiltonian. In practice, I don't know what to say here. I mean, I don't know what Hamiltonians really mean. In practice, physicists often deal with Hamiltonians that formally have infinite norms. Like if you look at a harmonic oscillator or something, it has infinite norm. Right, p squared, any of these terms has infinite norm, and so you don't actually get a threshold. And so this is an issue where you could say that the theory is just not complete, which is unfortunate because it's a realistic. I don't know if it's realistic, because even though the norms. Even though the Hamiltonians theoretically have infinite norm, in practice, I guess they don't really. Maybe, I don't know. But so I guess this is an area where we're sort of not really sure still whether fault tolerance is going to work in the real world, because in the real world there could be very high norm or even infinite norm terms in the Hamiltonian, and our threshold theorems don't allow for that. So there are some papers you can find by like I don't know how to pronounce it, Elixir, I think. He wrote some papers which are sort of skeptical of whether fault tolerance is ever going to work in the real world. Preskill has some papers where he tries to argue that it could work, but like it's not really settled, I think. Well, I think most people think it will work, but it's not formally proved, I guess. Okay, challenges for thresholds. I don't know. Yeah, so you can read this yourself. The lower bounds aren't as good as the estimates. I don't know if you care. The estimates are more important, maybe. Yeah. So this is maybe more interesting, which is that when you deal with stochastic noise, like probability p in a location fails, then I was saying p could be up to 10 minus 4 for Weir's proof, or 10 minus 3 for according to simulations, and it'd still work. But in fact, you often have noise that's not just with probability p. Instead, you have some Hamiltonian, or it's continuously rotated by an amount. It's continuously, your qubit is continuously rotated by some amount off. So it's like square root of 1 minus p0 plus square root of p1 or something. And unfortunately, so you can still prove a threshold, but the threshold for this kind of noise is usually quadratically lower. So instead of 10 minus 3, you're going to get 10 minus 6, or 10 minus 4, it'll become 10 minus 8 in terms of the norm of the Hamiltonian. And this is bad because a lot of the noise in real systems really is continuous over rotations or under rotations. It's not just these stochastic errors. So this could be quite sort of deadly, actually, I suppose, in the real world. I think most people observe that even though the noise is continuous, so here, let me briefly try to explain what's going on, right? So if your error rate is p, and you have n errors, right, n error locations, if you just have stochastic noise, the probability of any one of these locations failing is upper bounded by union bound by n times p, right? So it just goes linearly. Whereas if you have something like this, if you have if your error looks like e to the I p Z. Say that's your error channel, right? So it's an over rotation. It puts a phase of what is it? Sine whatever, sine P or something, which is roughly P for small p. But so if you apply this, okay, here let me try to explain this more slowly, more carefully. Right. So e to the IP. I'll put e to the IP x applied to get 0. Let's see what happens. So this gives me cosine p times 0 plus I sine p times 1. And this error term here, it's roughly, sine p is roughly p, if p is small. Okay. But now let's say I have n of these locations, and so, or maybe n of them occur one after the other, so I get e to the IP and x. Okay, yeah, this will be the same thing, right? So on 0, I get the same thing. Cosine np0 plus I sine np 1, and sine np is roughly going to be np. But you see, if you look at the amplitude of being in 1, here it's p squared. If you measure it, here you get p squared, whereas here you get n squared p squared. And so the error rate is actually growing like n squared times this, and that's the bad thing. When you have coherent noise, errors can add up quadratically instead of linearly. That's what I'm trying to say in some sort of non-rigorous way, but that's the issue, and that's why you get this quadratically lower threshold, essentially. Right. But in practice, we often don't observe this, and the reason is because here this only happens because the subsequent errors are adding up one after the other. So this is like e to the IPX times e to the IPX times e to the IPX times e to the IPX. But in practice, we often find, and we think that we find, is that coherent errors sort of point in random directions, and so they don't add up coherently, and they essentially just add up randomly, and so the directions don't add up, and so you just get square root of np here and n times p squared when you measure.
So the mean isn't 0, and the directions of the arrow don't add up to 0.
Right. So here what I'm saying is I have n errors that are pointing in the x direction, each of them with magnitude p, and they just add up. But no, I think, yeah. So in generally, you might expect that they're sort of pointing in random directions, and so that they would cancel out. But that would still it would cancel out an expectation, but if you look at the mean square when you measure it, it would still be so that would be the variance of the random walk, which is like square root of n. I'm just saying, or something, right? So if you have random walk on the line, the expected value is 0, but the expected value of the square is the variance, which is like n times 1/4 or something. Yeah, so it doesn't cancel out.